So as we start off this one, we talked about in the last video that we want to get approximations of area under a curve. And we did some under approximations, right? We'd split it up. We could do some under approximations. We could do some over approximations. In this case with a right hand point. We could do midpoint approximations and so on. Do the midpoint, the midpoint, the midpoint, and so on, right? These are all approximations. Well, to get more accurate with our approximations, you could split it up into smaller and smaller rectangles. So the widths are smaller and smaller. And hopefully you can see that, hey, you're going to have less error if I break it up into smaller and smaller rectangles. So ideally what we're going to do is then we'll just use a limiting process and take the number of rectangles to infinity. In other words, what we'll do is we'll take delta x, the width of the rectangle, to 0. That's the same thing. So as we take the number of rectangles to infinity, we'll eliminate our error involved. Well, this will involve our sigma notation. Okay, so we're going to play around with a little sigma notation first before we get into dealing more with areas under a curve for a second. So that's the Greek letter sigma. It's the uppercase sigma. It's the summation symbol. This would be the lower bound. Going up to n would be the upper bound. And then, whatever you have as your function. So let's do this first one over here. So you have the summation of 3i minus 2 from I being 1 up to 4. So that would be equal to, so I'll let I be 1, and then I'll let I be 2 in the formula, and then I'll let I be 3, and then I'll finally let I be 4, because I want to end with my upper bound there at I being 4. So let's go ahead and plug in that one by one. So I got 3 times 1 minus 2. Now I'm going to go 3 times the 2 minus 2. Again, I'm plugging it into 3i minus 2. And finally, 3 times 4 minus 2. And so we got 3 minus 2 is 1. Whoops. 1 plus 6 minus 2, 4 plus 7 plus 10. So we got 22. And that's the summation of 3i minus 2 from I being 1 up to 4. Is 22. Okay. Let's do the next one there with a negative 1 to the k, cosine kw, k pi. So we're going to let I be 1. Or in this case, I'm sorry, you don't have to use I all the time. In this case, we have a k, it looks like. Actually, let me just bring it down here. So if k is 1, plus, so here's k being 1. Now I'm going to let k be 2. Then I'm going to let k be 3. And again, it looks like our upper bound is 4. So we're just going to stop at 4. So I got negative 1 now is to the 2. Cosine k pi, so 2 pi. Negative 1 now is to the 3. Cosine of 3 pi. And negative 1 to the 4th. Cosine 4 pi. And so we got negative 1 times cosine of pi is negative 1. Negative 1 squared is 1. Cosine of 2 pi is 1. Negative 1 to the 3rd is negative 1. Cosine of 3 pi is negative 1. Negative 1 to the 4th is a 1. Cosine of 4 pi is 1. So it looks like I got 1 plus 1 plus 1 plus 1. So in this case, it just ends up being 4. Again, this is your sigma notation. Sigma notation. Let's go backwards now. So here we're given a series. And when I say series, meaning it's all being added together, right? We were expanding the series before. Here we're adding it up. So what would the formula be? So if I is 1, I would be 2 here, I would be 3, ... I would be 15 there. So hopefully you can see what number is changing each time. So we have the summation. So what's the formula? Well, the 5 stays the same. The 1 in front of the bottom stays the same. So it's just that I right there that's changing every time. And my lower bound, I'm starting with an I being 1, and I'm going up to that I being 15. And so there's our sigma notation for that series. Let's do another one here. Again, I like to write it below. Let me do it with k this time. So k is 1, k is 2, k is 3, k is 4, k is 5, k is 6, and k would be 7 on that last one. And do you notice how you have alternating signs there? So I have -1 7th plus 2 7th. Let me write it this way. Plus a -3 7th plus a 4 7th plus a -5 7th plus a 6 7th plus a -1 or -7 7ths. Again, k is 1, k is 2, k is 3, and so on up to k being 7. Now, how would I address the alternating portion? Well, if you remember this cosine k pi one up here, that will address the alternating portion. So if you have signs that alternate, you're either going to be -1 to the k or -1 to the k plus 1, depending on if you're starting positive or negative. Well, this one starts negative, -1 7th. So I'm going to use that -1 to the k. This one starts positive and then goes negative if you plug it in. So I'm going to have -1 to the k. Again, bless you. That'll address the negative part. And then we have the k over 7. And it's going from a k value of 1 up to 7. And you could test that, right? I'd say, okay, well, if k is 1, then be that. If k is 2, then be that. If k is 3, it'll be that. And so on, right? I check them all. That's my -1 7th. That's a positive 2 7th. That's a -3 7ths, and so on. And hopefully you can see, oh yeah, we got it. Right. Well, that brings us to the rules for these finite sums. So you can take that constant right there, you can put it in front, and you could of course add them up, you can split them up, right? And here's some formulas that are also very handy. For example, let me show you that one. Like, let's say we had the summation of I from I being 1 up to 3, right? So this would be if I was 1 plus if I was 2 plus if I was 3. So it'd be 1 for I, 2 for I, 3 for I, and you see how you get 6, right? Well, instead of doing that, these formula rules are real nice because they say, well, if I know this n right there, my n, then this will just be n squared, or n times n plus 1 over 2, in other words, n squared plus n over 2. And I just got to plug my 3 in. So it'll be 3 times 3 plus 1 all over 2. So 3 times 4 is 12 over 2, which is 6. Hey, see how it's the same thing? So these summation formulas are really nice because you know, if I don't go to 3, like 3 is no problem, but if I go from like I being 1 up to, let's say, 1,214, I don't really want to do that. I don't want to plug out, you know what I mean, and add them all up with that many times. There's no way. So I'm going to plug it into my formula. That's where the formula comes in handy, right? So you've got these formulas that you want to keep track of, 1, 2, 3, and 4 here, or keep them handy, right? And let's go here and let's use these properties and these summation formulas to do this. So I got the summation of 2i minus 3 from I being 1 up to 15. So this is my n right there, right? Let's use the property of, we can split this up. So 2i minus 3. And I'm going to put the 2 in front now. I'm going to put that in front. So 2 summation of I minus summation of 3. Okay. Now I'm going to say, and these are I being 1 to 15, I being 1 to 15. Now I'm going to be like, okay, this I is n plus 1. So I got 2, and then I've got the formula n plus 1 all over 2. But remember, n is 15. So I will put in the 15 for that. Minus 3 constant. So I'm going to be using this one right there. So minus 3 times, and notice it would be 3 times n, right? So n. I'm going to put in an n right now. So again, n is 15. So let's plug the 15 in. And so we got 2 times 15 times 16 all divided by 2. Notice the 2's cancel there. Minus 45. 15 times 16, got 240. So 195. Let's keep going with this one here. We got I squared. We got summation of I squared minus, I'm going to bring the 2 in front, summation of I cubed. This is I being 1 up to 10. I being 1 up to 10, so my n is 10. So I'm going to go up and look at my I squared up here. So my I squared is right here, right? So I got n plus 1, 2n plus 1, n plus 1, 2n plus 1, all over 6. And then minus 2, and then I go up and get my I cubed one. Let me go up here and get my I cubed, so I'm using that one. N squared n plus 1 squared all over 4. And then I recognize that my n is 10. So let's plug the 10 in. I got 10, 10 plus 1, 2 times 10 plus 1. Eleven squared, 121. It's all over 4. That's 1/2. So we got 23, 10 over 6 minus 121. 2. All right, now let's take a limit. Let's practice taking a limit on this. So we have limit as n goes to infinity. And we've got this 1 over n squared. And remember, we have an equation for this. And the equation was n plus 1 divided by 2. So we could go ahead and plug that equation in. And what we're doing here is we're practicing taking a limit as n goes to infinity, because what we're eventually going to work up to is letting our number of rectangles go to infinity, right? That's why we're practicing this with our sigma notation. So we're going to take the limit as n goes to infinity. Well, this is limit as n goes to infinity of, we got a 2n squared on the bottom. On the top, I got n squared plus n. And so we've got limit, common denominator there, of n squared over 2n squared plus n over 2n squared. So we've got limit n goes to infinity of 1/2 plus 1 over 2n. Well, if I run this to infinity, that'll go to 0, right? 1 over this huge number, 2 times infinity, if you will. That'll go to 0. So we're just left with this 1/2 plus 0. So this just ends up being 1/2. Let's do some more here. Limit n goes to infinity. I got 64 over n cubed. And then for this one, I'm going to use a formula again. So I'm going to use that I squared formula, which if you look at that, it'll give you n plus 1, 2n plus 1, and this is all over 6. So that's n squared plus n, 2n plus 1, all over 6. So we got 64 over n cubed, and I've got 2n cubed plus n squared plus 2n squared. So I got a 3n squared plus the n. This is all over 6. Limit n goes to infinity. Let me distribute the 64. So I get, oh, I'm sorry, hold on. Let me go 64 over 6. That'll give me 32 and 3. Let me do that. And now I'll distribute the 32. So 32 times 2n cubed, 64n cubed, plus a 96n squared, plus 32n. This is all over 3n cubed. And so we've got limit as n goes to infinity, 64n cubed over 3n cubed, plus 96n squared over 3n cubed, plus 32n over 3n cubed. So we got 64 thirds plus, let's see, 96 over 3 is at 32, plus 32 over 3n squared. As we run this to infinity, that denominator will get huge, so 32 over a huge number, that'll go to 0. That'll go to 0. And so we just end up with that 64 thirds plus 0 plus 0. So 64 thirds would be our solution there on that one. All right, let's do this last one, then we'll get into the limiting process involved for finding the area under the curve here. So we got the limit as n goes to infinity. I'm going to take that 2i times 2. I got a 4i. Whoops, this is summation of 4i. Over n times n is n squared. And this is I being 1 up to n now. And so what I'm going to do now is I'm going to take the limit as n goes to infinity. I'm going to put that 4 over n squared in front of the summation for I. See how that's still 4i over n squared? So let me use those properties. I being 1 up to n. Now I'm going to use the formula for that, which the formula is n plus 1 all over 2. So I've got limit n goes to infinity of 4 over n squared times that n plus 1 over 2. If you notice the 4 over 2, that'll give us a 2 right there. And then let me distribute that as well as distribute the 2. So we have limit as n goes to infinity of 2n squared plus 2. This is all over n squared. So I have limit as n goes to infinity of 2n squared over n squared, so 2 plus 2 over n. Oops, that's a 2n right there. 2n over n squared, which is 2 over n. That'll go to 0. So we're just left with 2 plus 0, which is 2. Well, as is written here, in order to find the area in a curve, under a curve, we're going to find the area of several rectangles and add them all together to get the total area, right? And so what we're going to do is we're going to find the width. So let's start out with the width of the rectangle as we introduced in the first video. We called that delta x, the width of the rectangle, and it was b minus a all over n, right? If you're going from a, notice we're going from a up to b, right? So it's b minus a all over n. N is our number of subintervals. So this is, in other words, how many rectangles I have. That's how many rectangles I have. N is the number of subintervals. And then we use the height. In this case, it looks like a midpoint here, but the height of each rectangle at some x, at some x value, or ci, will be f of ci. Okay, that'll be the height, f of ci. Okay, so we'll have whatever that height is, f of ci times this width, which is our delta x, right? The width of the rectangle. That'll be the area of that rectangle, right? And then we'll add up all these rectangles together. So number 3, to get an exact area, remember these were approximations. When we were adding all these up, they were approximations, right? We had some error. Either we were over approximating or under approximating. Maybe we were a little better with the midpoint. Who knows? Depends on the function. But to get an exact area, we need to add an infinite number of these rectangles together between A and B. So, in other words, we could do some of these rectangles, right? Maybe we do, here's some, and this is an okay approximation. But to get a better approximation, to get a better one, I got to go with more rectangles. Whole bunch of these rectangles, right? In other words, this delta x, that width, I want to run that. I want delta x to go to 0. And that will be a perfect area. So it's a limiting process. Well, as delta x goes to 0, what I'm doing is, right, if I want delta x to go to 0, then what I'm going to do is I'm going to let the number of subintervals go to infinity. That will cause it to go to 0. So it's a limiting process here, right? So we want delta x to go to 0 or the n to go to infinity, right? The number of subintervals to go to infinity. So the area under a curve, and with the requirement that it be above, it's the area under the curve, but it's above the x-axis, okay, is the limit as n goes to infinity of the summation of the height, f of ci, times the delta x, from I being 1 up to n. So this right there is the height, of the rectangle. That delta x right there, that's our width of the rectangle, right? So we're summing them all up. We're summing them all up, right? Summation symbol there, the sigma. Summing them all up, and we're running n to infinity. In other words, delta x, the width is going to 0. So it's getting this perfect, if you can imagine that, a perfect area, right? And I would make a note here. Delta x, as I mentioned, is b minus a over n. And I also mentioned that ci is a plus delta xi. That's where your ci will be. Alternatively, some textbooks, some professors will also use k with this. So they go limit as n goes to infinity, k being 1 up to n of f of ck delta x. But same thing, I is k's, doesn't matter. Ck is a plus delta x k. All right, let's do some problems with that. All right, so here it says find the formula for Riemann sum by dividing AB into n equal subintervals and using the right endpoint for each ck. Then take the limit as n goes to infinity for the area under the curve for 1 plus x squared. Let me see if I can give you a kind of a picture of this as well. We're going from 0 to 3. Two comma 5, 3 comma 10. So this is kind of that 1 plus x. Whoops, I did that wrong. I'm sorry. 0 comma 1. Sorry about that. 1 squared plus 1 is 2. 2 squared plus 1 is 5. 3 squared plus 1 is 10. There we go. Okay, so we're trying to find this area, right, from 0 to 3. That's our A to B. And we're taking these rectangles, but we're taking these widths, delta x, going to 0. So we're going to take more and more rectangles and add them up, right? So we're going to go, we'll find that area. Well, let's start out with delta x. Let's find the width of each rectangle. So delta x would be b minus a, again, a to b. So 3 minus 0 over n. So our delta x, our width of each rectangle is 3 over n. Number 2, the ck, so that this is the x value, where we're going to take the height for our equation for the f of ck value. So a plus delta xk. So our ck is, a is 0, delta x is 3 over n times k. So our ck is just 3k over n. So area under a curve above the x-axis is the limit, and goes to infinity, of the summation of the height of the rectangle times the width, delta x, from k being 1 up to n. And subintervals, again, we're running the number of rectangles to infinity. In other words, delta x is going to 0. So this will become limit n goes to infinity, summation f of ck, so that's f of 3k over n, times delta x, our delta x is 3 over n, k being 1 to n. Now let's do f of 3k over n. Remember, f of x was 1 plus x squared, or x squared plus 1. All right, so we got to plug that in. So we got limit n goes to infinity of 3k over n goes in for x. So I got 1 plus 3k over n squared. That's the 1 plus x squared. Delta x is the 3 over n. K being 1 to n. So limit n goes to infinity. We got 1 plus, oops, that other way I got. One plus 9k squared over n squared. This be multiplied by 3 over n. I'm going to put this 3 over n right there in the front there. Remember, n's going to infinity. Limit n go to infinity. So I got 3 over n. And then I got summation of 1 plus 9k squared over n squared. K being 1 to n. So that'll be, limit as n goes to infinity, 3 over n of summation of 1 plus the summation of 9k squared over n squared. So I'm going to put the 9 over n squared out front, and then I have the k squared right there for my formula use. So I have limit n goes to infinity, 3 over n times, and this is k being 1 to n. This will be the constant times n, so 1 times the n. Then I look up, for this one, I look up the k squared. That's that I squared formula. So I'll have the 9 over n squared will stay there, but then that I squared formula will come in. So I'll have n plus 1, 2n plus 1. This is all over 6 if you look back at that formula. Okay. So we got 3 over n times n plus, let me make this 9 over 6 as 3 over 2. So I got 3, and I'm going to multiply that n plus 1, 2n plus 1. And I'll take that 3 through. Two n cubed plus 3n squared plus Now let me take the 3 over n through to both of those. So I'll have 3 plus 18n cubed plus 27n squared plus 9n. This is all over 2n. Now it's to the third. So that's 3 plus, now I have 8n cubed over 2n cubed. So that's 9 plus 27n squared over 2n cubed, so that's 27 over 2n, plus 9n over 2n cubed, so that's 9 over 2n squared. Now I run this to infinity, so that'll go to 0, that'll go to 0. So I'm just left with 3 plus 9 plus 0 plus 0. So this exact area under the curve, let me come back up here. This area under the curve in yellow is 12. Exactly 12. All right, not an approximation. Exactly. Let's do another one. All right, here we've got, let me give you a picture again. I got 5x. I'm going from 1 to 3. Let me just go by 5. So 1, 5, 2, 10, 3, 15. Right, here's the line. I'm just showing part of the line, of course, because I'm trying to figure out this area from A to B, right, from 1 to 3. What's this area under the curve here, right? Of course, it is a geometric shape, so we'll talk about doing it that way. But let's go through it with the calculus first. Number 1, what's the width of each rectangle? B minus A over N. So in this case, my A is 1, my B is 3, so I got 3 minus 1 over N. So my delta X is 2 over N. Number 2, whereas each X value would be A plus delta X K. So that would be 1 plus delta X is 2 over N K. So my CK is 1 plus 2K over N. Area under a curve above, notice I say it's got to be above the x-axis though, is limit as n goes to infinity. So the number of subintervals going to infinity of the rectangle height times the rectangle width, delta x, from k being 1 up to n. So that's limit as n goes to infinity of summation of f of 1 plus 2k over n times my delta x is 2 over n. So I'm going to plug the 1 plus 2k over n into f. Remember, f of x was 5x, right? So this will be 5 times 1 plus 2k over n. That's my f of xk, and then my delta x is the 2 over n here. All right, let's put the 2 over n in front. So I got 2 over n summation, and then let's take the let's take the 5 out in front too. 5 and the 2 over n. So let's make that a 10 over n. And so I just got the 1 plus 2k over n here. Ten over n, and then that'll be a summation of 1 plus a summation of 2k over n. So I'm going to put the 2 over n right there, 2 over n, and put the k right there for the formula. So there's my 2k over n. Again, k being 1 to n, k being 1 to n. And so this is 1 constant times n. All right, so I use that formula there. Plus 2 over n. I use the formula for I, which was n plus 1, or k in this case I used. But over there. Let's go ahead. Actually, I'll just take it through right now. Let's take that through. So I got 10n over n, that's a 10, plus, and then I got 20n squared plus 20n all over 2n squared. And notice that will go to 0. So we got 10 plus 10 plus 0. So this is 20. So that's saying that area up here, right, I had in red, or I'll do this area is 20, right, between 1 and 3. The area under the curve of 5x is 20. Exactly 20. And here we've got x plus x cubed. So you got, let's see, 0, 0, going up to 1. Let me spread that out a little bit. So 1 would be 1 plus 1 cubed. So 2. Anyways, you graph a few points or something like this. Just give a curvature to it. We're just trying to find this area between 0 and 1, right? That's what we're trying to find. Delta x, width of each rectangle b minus a over n, a and b. So delta x is 1 minus 0 over n. So delta x is 1 over n. Number 2, ck is a plus delta xk. So ck is a is 0 plus delta x is 1 over n k. So ck just ends up being k over n. Number 3, the area under the curve above the x-axis. Again, this is always above the x-axis. So limit n goes to infinity. Summation f of ck delta x. F ck being the height of the rectangle, delta x being the width of the rectangle. So this is limit as n goes to infinity of the summation of f of ck. Well, that's k over n. And delta x is 1 over n. K being 1 to n. And so this will be limit n goes to infinity. And remember, our f of x was x plus x cubed. And so it'll be k over n plus k over n cubed. That's our f of x, k. And then our delta x is just 1 over n. Let me put that 1 over n in front of the summation. So we got limit n goes to infinity, 1 over n summation, and I have k over n plus k cubed over n cubed. So that's limit n goes to infinity, 1 over n. And then let me split this up. So I'll have 1 over n summation of k plus 1 over n cubed summation of k cubed. K cubed over n cubed. Okay. And then summation of k, so that would be our summation I, right? So it would be the n plus 1 all over 2. And then I look up the I cubed formula, or k cubed formula for that one. And it gives me the n squared, n plus 1 squared all over 4. So you got n squared plus n all over 2n plus, let's see, that'll be n squared times n squared plus 2n plus 1. So that'll be n to the 4th plus 2n cubed plus n squared all over 4n cubed. Let me take the 1 over n through out front. So I have n squared plus n all over 2n squared all over 4n to the 4th. And so we've got n squared over 2n squared. So n squared over 2n squared plus n over 2n squared plus n to the fourth over 4n to the fourth. One half plus 1 over 2n plus 1/4 plus 1 over 2n plus 1 over 4n squared. That'll go to 0. That'll go to 0. That'll go to 0. So it looks like I got 1/2 plus 1/4. Which is 3/4. That's the area under the curve between x plus x cubed, that function between 0 and 1. Thanks so much for watching. We'll see you guys next time. Hope that helps.